Hi, here we are discussing about a project image encryption design using FPGA. Here, the image encryption plays a crucial role in securing digital communications, especially with the rise of cyber threats and data breaches. So, this research focuses on implementing a Chaos-based pseudo-random number generator for image encryptions and compose its performance with a Fibonacci and Galois-based linear feedback shift register. The proposed systems is developed using a Verilog HDL and synthesized on Xilinx Spartan-6 FPGA with a real-time TFT display interface for encrypted and decrypted image visualization. The traditional LFSR-based PRNG are widely used due to this simplicity and speed. However, they suffer from predictable periodicity and lower security strength. In the contrast, the Chaos-based PRNG provides a higher randomness and security, making them ideal for cryptographic applications. So in this work, the different PRNG approaches are analyzed based on the randomness quality using the NIST test suite with the hardware resource utilizations and encrypted security. The Chaos-based PRNG is then integrated into the stream cipher encryption systems, so where the image pixels are transformed bitwise XOR and chaotic substitution operations. The encrypted image are decrypted using inverse transformations and displayed it on a TFT display, ensuring the real-time validation. This work demonstrates a practical hardware-based image encryption system suitable for real-time and secure multimedia applications such as IoT, medical imaging, and defense systems. Further enhancement including optimizing a Chaos-based PRNG for high-speed cryptography applications and exploring AI-based encryption technique for enhanced security. Okay, so now we can verify the paper. So this paper is fully designed for the image encryption design using for joystick method. Okay, and we have also designed for the image decryption. Okay, the basic architecture of this paper, it will be come with the figure 1 image encryptions and decryption. Okay, so here the startup with start system initialization, read image data and image to noise data, and the joystick equation encryptions and the next frames input images. Okay, so this is a method, this is a reverse operations. Okay, so again read the encrypted image. Okay, and again they are doing for the joystick equation transformations with the XOR based encrypted method. Okay, so here this algorithm chaotic with the image encryptions they have done using a bitwise logical operations. Okay, and tuning with the bitwise method. Okay, but we have used the additional architecture of the Chaos based bitwise dynamical pseudo random number generator on FPGA. So this paper supports the parameter based bitwise supports, and it will be highly optimized one for chaotic method. Okay, so here you can verify the architecture. Okay, so this basic PRNG the construct with the chaotic method architectures with support of the 5.4. It will be periodically initiating the parameter tuning to the LFSR architecture. Okay, as per the configuration data, and this enhanced PRNG, it's not repeating the same LFSR sequence. Okay, so it will be generating different sequence. It will be highly secure for the cryptography applications. Okay, so if we use this in a image encryptions, our image it will be come with the very highly secure and lightweight hardware implementation. Okay, so now we have implemented this work in Verilog HDL and synthesized on Xilinx Spartan-6 LX9 FPGA, and this work also developed in a hardware implementation. Okay, so here the first of all we read the image. Okay, image data here. Okay, so read the image data and it will be converted into the hexadecimal file. That hexadecimal file it will be loaded into the 5.4 memory or any block memory. Okay, so then we read the data. Okay, and parallelly we run the joystick method. Then we need to encrypt the data, and then encrypted data also we need to shown. Okay, and that encrypted image we need to again decrypt with using the same method. Okay, and we need to show the decrypted method. Okay, so this is one of the flow. Okay, so now we can verify the flow of the work step by step. Okay, so here this is the image UI. Okay, so here we can choose any images. Okay, so butterfly or line. Okay, so whatever images you are needed, you can choose it. Okay, then you can run the simulations. Okay, before that we need to verify the Verilog HDL coding. So this is a Verilog HDL coding for yeah, this is a simulation method. Verilog HDL coding for the simulation method. Okay, so image encryptions and decryptions. Okay, so here image encryptions done with the Chaos-based PRNG. Okay, and this work also compared with the Galois and Fibonacci based LFSR sequence in the basic PRNG architecture. Okay, and yeah, initially we start with the image encryption. Okay, and it will be generated the hexadecimal file. So based upon that hexadecimal file, here it will be generated. Okay, so input image, here it will be generated. After that we need to run the simulation. Okay, so this is the simulation output. Okay, so image encryptions, Jaws PRNG. This one is the image encryptions and this one is the image decryption part. Okay, and this is a control for encryptions and decryption method. Okay, so here the image encryption decryption algorithm. Here the first of all we read the data. Okay, using a read address we read the data. Okay, so this is our read data. So depends upon your image, it will be differ. Okay, so here data, it will be start with a 908D 8D 8F8D. Okay, so the parallelly we run the PRNG method. Okay, so the PRNG output it will become here 80, 145, 164 and 234. So this is it's a separate code. So this is a code for Chaos-based PRNG Fibonacci series. Okay, chaotic input configurations and enhanced PRNG method. Okay, so as per the base paper architectures we have developed it. Okay, and this simulations separately we can show. Okay, so this is a PRNG method. Okay, so initially the data we need to load into the FIFO memory. Okay, so for periodical initializations of the seed value. Okay, so here this is a configuration data 52, 72, 48, 32, 77, 66. Okay, so the periodical initialization means that the read enable it will be initiate at the periodic time. Okay, so here you can analyze it. So the time period of the periodic is a 100 clock cycles we have used. Okay, so read delay, that is a read delay. Okay, so the periodically it will be initiate the FIFO memory and it will be initiate the randomness. Okay, so as per that the random bit it will be generated here. Okay, so here we can plot the data with using analog waveform. Okay, so here you can check it. So this is a random sequence. Okay, so how much time we will run. Okay, so it will be generating the random data. Okay, it's not stoppable. Okay, okay, so here we have used 128 cross 160 in TFT display and 256 cross 256 for simulation model. Okay, so here we are initially loaded the data, right? Okay, okay, with the joystick method, and yeah, here we are initially loaded the data. It will be generating the PRNG method. Okay, so here this PRNG output, so PRNG output XOR with the read data. Okay, so 8D and A4 it will be XOR. That XOR output we need to give to ENC write data. Okay, so example you can analyze that in a calculator. Okay, so here the 8D XOR with A4, 8D XOR with A4. Okay, so the output is 29. So here the read and write data. Okay, so encrypted write data it will be storing at 29. Okay, that value we need to store into our write memory. okay, that is the encrypted memory. Okay, so after that process completions, okay, so we initiate the encryption done. Okay, so then only we start the image decryption process. So image decryption process, again it will be encrypted, again it will be XOR the data. Okay, so here it will become 29 means it will again encrypt the data, so then we will get a original data. Okay, so with the same PRNG output. Okay, so here okay, so here you can analyze it. So 29 and PRNG output is A4, the original value is 8D. Okay, so the previously we XORed with the 8D XOR A4, we will get 29. Okay, now we will XOR 29 with the A4, we will get 8D. Okay, so this is a decrypted data. Okay, so this data will be stored into the original memory. Okay, that is a decrypted memory. Okay, so this is a flow of the work we have done. Okay, so with the Chaos-based PRNG method. Okay, and this work we have done with the Xilinx with the two different LFSR architecture. So one is for Galois-based LFSR, another one is a Fibonacci-based LFSR. Okay, so this is a Xilinx synthesized report. Okay, so here you can analyze the Fibonacci. It will be take around 380 in slice registers, LUT 599. Okay, so features, okay, so IOB. Okay, and synthesis report we can analyze with a delay. Okay, so 13.808. Okay, and we can analyze the RTL schematic. So this is the image encryptions and decryption method. So image encryptions we have used the Chaos method, Chaotic, okay, and controller for encryption. Okay, and this is the XOR gate. So this is for the PRNG method for enhanced PRNG and Chaotic input configuration. So this is for the enhanced PRNG method with the basic PRNG, FIFO memory, MUX and multiplexer. Okay, so here this is a PRNG method. Here it will be choose with the PRNG accumulators. Okay, and also the Fibonacci LFSR. Okay, so the Fibonacci LFSR come with, okay, so this type of architecture. So it's completely D flip-flop based LFSR architecture. Okay, and after this part we can analyze the simulation output. Okay, so now once the simulation executed, okay, so we can load the output image. Okay, so here the two different output images we have loaded into the hexadecimal file. Okay, so one is for encryptions and one is for decryption. Okay, so this is an encrypted image. Okay, so here you can analyze it, encrypted value. After that we can analyze the output hex. Okay, so this is a decrypted image. Okay, so whatever image you are needed, you can give an input and you can check the output here. Okay, so after this process we can check the same work in hardware implementation. Okay, so here we have generated this work in Spartan-6 LX9 FPGA. Okay, so here you can analyze it. Okay, so with the TFT display board. So this is a Chaos PRNG. Okay, that image encryption PRNG Fibonacci it will be added. Okay, Fibonacci method this one is. So this is a TFT display interface. Okay, so these are the internal memories we have used, and this we are already saying, right, image encryption and decryption method. Okay, so these things. Okay, so here we have used a selection based one with the using support of the multiplexers. Okay, here we have configured the selection point. Okay, so here 01 means encryptions and 10 means original images and 00 means decryption. Okay, so as per that we can verify our data in a hardware implementation. Okay, so here first of all we will verify the butterfly images. Okay, so here you can verify the hardware image output. Okay, I think it will be shown clearly. Okay, so here this is a start signal we have used. Okay, and this one is a reset button. Okay, so if you give reset, it automatically image gone. After if you reset high, so it will read the image from the memory. Okay, and here this is a start button. Okay, so once you are start up encrypted, it will be encrypt the data, and the two LEDs we have used for encrypted done and decrypted done. Okay, so this two pins we have used for the selection mode. Okay, so initially you are chosen a 1 and 1, you can go with the reset. Okay, so it will be showing the completely FF output only. Okay, so after that you can give any one of the signal. Okay, so first of all you plan for the original value. So original value means we need to give for the 0 1. Okay, so here this one. Okay, so here you can analyze it. This one is this one is the encrypted value. Okay, encrypted image. Okay, and can now switch on. This one is a decrypted image. Okay, so this one is a decrypted, and 0 0 means you go with the original. Okay, so original and encrypted. Okay, so after that it will become with the decrypted. Okay, so as per that we can verify the hardware implementations output. Okay, yeah, after this hardware implementations we can verify the comparisons part, the image comparisons. Okay, and Xilinx comparisons we can take it. Okay, so it will be come with Chaos-based PRNG, Fibonacci and Galois, and image encryption Chaos PRNG. Okay, Fibonacci and Galois, and this one is a image encryption and hardware. Okay, so totally 6 comparisons. Okay, and these are the image comparisons we have done. Okay, so you can verify the train images, encrypted images and decrypted images, and with the PSNR and SSIM values we are compared, and this is a lion. Okay, and we can analyze this data sets. Okay, so here we have used DI V2K train LR bicubic data sets. Okay, so it will be have more number of images. Okay, so we can give any images and we can check the output. Okay, so it's not a problem here. Okay, so then this is the abstract document for this project. Okay, title, best paper abstract, improvement of this project, existing system, and image encryptions and decryptions, related nodes, disadvantages, advantages, proposed systems. Okay, and chaotic method based nodes. Okay, and introduction notes, the comparisons between the Fibonacci LFSR and Galois LFSR. Okay, yeah, it's covered 29 pages, and the literature survey, finally it will come with the references. Okay, thank you.
Introducing NXV Innovation, your trusted partner in IP design and VLSI research. With over 300 plus completed projects in cutting-edge domains like low-power VLSI design, high-speed data transmission, signal processing, and secure networking, we offer tailored solutions for students and professionals in BE, BTech, ME, MTech, and PhD programs. At NXV, you not only get expert-guided projects starting from RIS 6000 Transparency, but also enjoy unmatched benefits like RIS 1000 to off on your second project, free documentation, and easy-to-understand video explanations. Plus, our rewarding referral program lets you earn up to RIS 2000 MANTs for every successful referral. Trust us to simplify your research journey with high-quality, affordable, and fully customized VLSI solutions. Visit our website to explore a comprehensive collection of projects, organized year by year from 2014 to 2024. The latest 2024 research projects are now available for publication, along with several 2024 non-completed titles, which are updated monthly with new possibilities. For application-based projects, interface designs, and mini projects, you can also rely on NXV for top-quality solutions. We provide exceptional PhD assistance with full publication support and offer an installment payment option allowing you to pay module by module. Let NXFee guide you through your research journey with flexibility and expert support. Thank you.